Hello, everyone, and welcome back to another episode of Solidity Fridays. Today, I'm joined by Myles and we are continuing our SuperFluid series. We have been comparing different streaming apps and protocols in Solidity, and SuperFluid is our favorite, so we're diving deep into their code. Myles, how are you doing?
Hey, morning, Tam. Yeah, I'm doing well this morning. Looking forward to diving into our third part of the series.
Yes, in this module, we'll be looking at SuperApps, and they are programmable cash flows, basically.
Sweet.
So,
Yeah, let's dive in.
yeah, cool. So SuperApps allow us to build smart contracts that are fully integrated with SuperFluid at the protocol level. If you've looked at our tradable cash flow tutorial or user data tutorial, we are using a SuperApp in each of those sample applications. So you have the incoming streams, then your custom logic of your SuperApp, and it can really be anything, and then outgoing streams. After we look at this, maybe, so I don't know if you know, but SuperFluid has I think it's called Wavepool. It's a ongoing hackathon, and it has different cohorts like all the time, and they judge people's super apps, and you can win cool prizes. So after you watch how they work today, and then next week we'll look at some examples of how they would build a super app. Then maybe viewers can start building their own and sending them to SuperFluid and tagging Solidity Fridays as inspo.
Yeah, that's a great idea.
So you receive a stream, and then use special callbacks within that super app to automatically open up the new stream from the NFT to the owner of the NFT. The contract listens for a call to a SuperFluid super agreement contract. In this example, the constant flow agreement contract. Remember, there are two types of agreements, the constant flow and the IDA. The constant flow is these streams, and they flow constantly for the whole duration. And then the IDA is, what does it stand for again, Myles? Instant Distribution Agreement.
That's it.
So it's one payment to many recipients, and it's instant, and it is not ongoing. But so you can use either, and your contract listens for a SuperFluid agreement contract and runs a single callback function in response to the following three actions. So firstly, a flow is opened with the super app as the receiver, or a flow is updated, which has the super app as the receiver, or a flow is closed by the super app's counterparty. That is, if either the sender of a flow into the super app or the recipient of a flow from the super app deleted the flow, a callback will be run. As of today, this is only relevant for the case of canceled flows. So SuperFluid's doing a lot of upgrades and things behind the scenes. So this, as of today, is very telling. New feature, maybe. When a stream is created into a super app, the before agreement created and the after agreement created callback may be run, and we'll see these in the code. These callbacks can execute any arbitrary logic as long as this logic fits within the rules of standard smart contract developments and the rules of super apps, which are explained further later in the section. In the case of the tradable cash flow contract, that example they're talking about, the logic we included inside of the after agreement created callback will open up a money stream from the app to the NFT's owner in an amount that is equal to the flow rates into the app. Remember, we saw the flow rates when we were looking at the CFA, which was our first episode in the series. You don't have to watch them in order, but yeah, you might have. But if not, and you want to know about the flow rate, that's covered in our first episode of the series. Super apps like the tradable cash flow example keep their callback logic simple, while others get more advanced and leverage items like user data for additional functionality. That's cool. Cool. I'm just going to have this open, but we don't need to go through it, I think. So we have the callbacks.
Yeah, let's look at that.
Callbacks are run when a super app is on the receiving end of a transaction that creates, updates, or deletes an agreement in relation to that app. The constant flow agreement and instant distribution agreement activate different callbacks in different scenarios. In the following table, the constant flow agreement is referred to as CFAV1 and the instant is IDAV1. Okay.
So these are just custom hooks for when
Yes.
before and after logic to be created. That's
Yes, based on the stream conditions. I don't know if you want to go through the conditions and the callback that gets called, or if you want to just go through the different conditions, or should we just go into the code and when we see one of these being used?
Yeah, I think let's just dive into the code and then
Cool.
we can come back to this.
Cool. Yeah, they get into code here anyway. So it's in packages, Ethereum contracts, apps, SuperApp base, and that is inheriting SuperApp. So perhaps we should look at that interface first. What do you think? It might have some errors.
Yes, always love looking at the interface first, especially because they're NAT specs in the interfaces.
It is. SuperApp, there you go. So it imports iSuper token. And then they say, beware of the app being jailed when the word permitted is used.
Interesting.
Obviously, they don't, they mean word as in like the bytes.
The bytes array.
Okay, so it doesn't have any custom errors here. And then this is just the NAT spec, but we'll bounce between. Okay, so the first function is before agreement created. And we're going to see the NAT spec in the interface. This is callback before a new agreement is created. It takes in a super token used for the agreement class address.
So the agreement class would be CFA
or IDA, yes. So those are deployed by SuperFluid, and you just find the address. I wonder where they are, those addresses. Maybe it's in the README of the monorepo. The agreement class address, then the agreement's ID, and the agreement data, non-compressed. Then the context data. Yeah, it's important to have context in this context. Then it returns CB data, a free format in memory data the app can use to pass arbitrary information to the after-hook callback.
Awesome.
Very cool. It will only be invoked with static call. No state changes are permitted, and only revert with a reason is permitted. I see. And then if it doesn't do these things correctly, I think that's when you get jailed. Cool. Okay, so yeah, this makes sense because for this super token, with this agreement data, and let's say a CFA, I can have many CFAs running
concurrently.
Concurrently. So you'll have many IDs. External view, virtual override returns bytes memory, CB data. And then it reverts unsupported callback before agreement created.
So it reverts with the reason string.
Yes.
Okay.
If the callback doesn't execute like successfully, then after the agreement is the same. Yeah. And then before agreement updates, it takes in the same. And then in this agreement data, bytes call data, we looked at that in the agreements we looked at, and there'll be permissions encoded in here through bit mapping. So you'll probably need to give permissions to the app in the agreement data. Cool. And then after agreement updated, and then before agreement terminated, and after agreement terminated. Cool. So when you're building a super app, I assume you inherit this contract.
Yes.
So my contract is super app base.
Yes.
And it inherits this abstract contract. Cool.
And then you have to implement these hooks.
Absolutely, yeah. And then you can add your own custom logic.
Yeah, that's pretty awesome. So you could
I
say,
don't even know this license.
yeah, I've never seen that license before. Interesting. So for instance, you could say
Free copyleft.
before app is created, transfer in a lump sum into the sender's account. A lump sum ready to be distributed.
Yes.
That's really cool.
Yeah. I wonder if on SuperFluid's site, if they have any examples of super apps that you can interact with. This is obviously the main SuperFluid app.
Yeah. I've only seen their tutorials where they can demonstrate how CFA and IDA work.
I wish we had a list of
apps that run on top of SuperFluid.
Yes, and there probably is. You could probably find it through the winners of like the wave pools on.
I think there's an ecosystem tab, so we could look at that.
There is. What's this?
Partners.
That's cool. So they're also working as an accelerator, as if they don't do enough. Okay, that's not what we're looking for, but good to know if you have a Web3 project and you want to hypercharge it, you could contact SuperFluid. Oh, this is a video. Sorry. Cool. So yeah, these are the anatomy of the SuperApp callbacks, and then I wonder if they show. Okay.
Yeah, they're just breaking down the
Break down each variable. Calling agreements in SuperApps. There we go. So there's call agreement and there's call agreement with context, which I think would be more used. So if you're making a call to a SuperFluid agreement inside of a SuperApp callback, you should remember that you need to receive a context and return a context by using call agreement with context function. If you are not making this call inside of a SuperApp callback, you should use call agreement. But when would you be not making the call inside a SuperApp callback? I guess you'll see. Cool. So when calling the host contract to trigger actions related to the constant flow agreement or the IDA, you may use either of these two options. Both of these functions allow you to pass in an encoded call to the agreement you'd like to interact with, as well as an optional user data value. The call agreement with context function will perform the same actions as the call agreement, but it will also enable you to pass in a new context value, abbreviated to CTX, to your function call. If you run call agreement with context outside of a super app, then call agreement with context will fail due to this statement. Require context.app address equals message.sender and probably SuperFluid call agreement with context from wrong address. So yeah, this is quite important if you're building a super app to use call agreement with context and not call agreement.
Could it be that you just like an arbitrary contract that uses a SuperFluid contract and not say a super app? Then you would use.
Then you would get the wrong address. So and why that would happen, I think, is if you're not inheriting super app base. So in that context, you'll get the app address, and it has to be the address calling this call agreement with context. And if that's not the case, then it'll revert. Yeah, so it says call agreement with context is primarily meant for use in super app callbacks. Each super app callback will be passed a context value from the host contract, as the SuperFluid host contract is the caller of each callback. Yeah. This context value is what needs to be passed to any call you want to make to the SuperFluid host contract inside of your callback. This goes for all operations which create, updates, and delete flows in these callbacks. So yeah, as a reminder, the logic within this host contract can be found in SuperFluid.sol. So now we know what to inherit, and let's maybe look at SuperFluid.sol's code. That's in Ethereum contracts, SuperFluid.sol. It's just such a large repo. I don't usually say my path, but oh, cool. It uses the universal proxy, the UUPS proxy.
So this is the brain of the operation.
Yes, this is the brain, and I've been looking forward to the last 2 episodes covering this. And yeah, it's interesting that this is fixed at 0.8.16, but then the SuperApp, because you're going to inherit it in many versions, it's set to anything above 0.8. Cool. So it imports everything basically. iSuperFluid governance, which we spoke a bit about last episode, iSuper agreement, iSuperApp, SuperApp definitions, context definitions, batch operation, SuperFluid governance configurations, iSuperFluid token, iSuper token factory, and IERC20.
Wow.
All from iSuperFluid. Okay, cool. So we should also have that open on our interface page because that's where we'll get our NAT spec.
There it is.
Cool, and it imports these things from definitions.sol. I'm wondering though if I'd actually just love to look at definitions.sol quickly. I'm getting distracted though. Let me know if I'm going to
the rabbit hole.
It might be in contracts, agreements, definitions. No. Apps definitions. No. Utils probably. Huh. Oh, there's a batch liquidator. Ooh.
Oh.
I wish I hadn't seen that. Now I want to do a whole nother episode.
Up to.
Up to, thanks. Libs.
Yep.
We checked in SuperFluid, but okay, my bad. I don't know where it is. Let's just check its definition. It's in interfaces. Cool. App level is a way to allow the app to whitelist what other app it can interact with. For more details, refer to the technical paper. That would be an interesting read. Cool, so there's different masks for app levels and final and second. Cool, these are all constants. Then these are all the bit masks. Oh, have we looked at this before? Oh, yes, and then the app jail reasons.
Yes. Briefly looked at this last week.
We did look at this, yes. Okay, cool. Library context definitions. And then are the other ones? Yeah, they're libraries. Okay, I was just wondering what these were. Are they libraries? And they are libraries. So it imports these libraries from definitions.sol, which I think was an abstract contract. Cool, so there's these errors. These are the custom errors, and you can find them in the interface. I don't want to spend too much time going through each one. App-related custom errors, error app rule code, unit 256. Oh, okay.
That's the jail reason, okay.
Okay, they're funny too. I'm really enjoying this repo.
Me too.
I think we got really lucky because we always want to do part 2s, and our first series we chose a really good repo.
Good way to start the series, yeah, definitely.
Cool. It supports call utils, which makes sense because we're doing calls and callbacks, and base relay recipient. Cool, so it's UUPS proxyable, iSuperFluid, and base relay recipient. I'm wondering if we should look at that.
Yeah, I suppose we could give it a quick brush over.
A base contract to be inherited by any contract that wants to receive relayed transactions. A subclass must use message sender instead of message.sender. Cool. I wonder why this is. We'll see in the code maybe. So oh, it's just these two things. And function checks if the forwarder is trusted. You put in the address and it'll return true or false. This get transaction signer is returns if the call came through our trusted forwarder, return the original sender, otherwise return message.sender. Should be used in the contract anywhere instead of message.sender. Okay. And that's where they check.
So it's basically contracts passing data to each other when you use this.
Okay, cool. Cool. I scrolled too far. Using save cost for you in 256. Always a good practice. Then there's a struct called app manifest, which is in 256 config word.
Interesting. Just a single object in the struct, a single variable. I'm sure we'll find out why they do that.
I don't know if we will. There's a reason. I've learned it before on a previous Solidity Fridays, and now I'm just trying to remember. I think it's a storage thing. Who was it? Where had I seen this before? I think it was in OX Monaco.
I've seen it before too. I just can't remember what the reason was for them doing it. I think you're right. It's something to do with storage or packing, data packing or something.
Yeah, or it has to do with I think I remember one of the things I was looking at, and then they said one of the people who wrote the code said that it had to do with the compiler. That compiler read it easier when it was like app manifest.config word.
Yeah.
But I'll reread that comment and then I'll comment on this YouTube when this is uploaded to YouTube.
I think it was Nick Mudge who was saying that.
Yes, I think you're right. Interesting.
Shout out to Nick Mudge. Thank you very much.
Yeah, such a good guy. Cool. Some immutables, non-upgradable deployment, and app whitelisting enabled. Those are two bools. Then we have the maximum number of level apps. Sorry, the maximum number of level of apps that can be composed together. 1. So you can only compose 2? 2,
yeah, exactly.
It's interesting that it's uint here because that means uint 256 and you're just having a 1. You could do uint 8 maybe. Unless they might do some bit shifting with it later. So they're saying to do composite app feature is currently disabled, hence app cannot. Yeah, so you can only have one app, but soon composite apps will exist.
That's going to be amazing.
Wow. Callback gas limit, 3 million. Warning, never reorder variables. Always double check that new variables are added. Append only. Reordering variables can permanently break the deployed project contract. Yeah, so this is a UUPS thing. If we have time at the end of the episode, I actually have a page open with the UUPS, like how you can create a data collision. And that's what they're talking about here, is you can only append only and never reorder your variables, because then you'll point 2 things to the same slot maybe.
2 different things to the same slot.
I'll send it to you. If we don't have time in the episode, I'll send it to you, Myles.
Yes, please.
Cool. Then there's an instance of iSuperFluid governance and an array of iSuper agreements, because remember, you can have multiple agreement classes. Then bytes 32 to uint of the agreement class indices. iSuper token factory, iSuperApp to app manifest. That's cool, and it's internal app manifests. Then the next one is composite app whitelisting, source iSuperApp to target app to is allowed. Cool.
Oh, cool. So I suppose that's just set to false right now.
It is, yeah.
Yeah, that's cool.
Or it might be that this is 0, or like, you know.
Yeah.
It's because if there's nothing in the mapping, it says this is 0, I think, the first. Then there's a context stamp of the current transaction. It should always be cleared to 0 before transaction finishes. Yeah, that would be important. If app whitelisting is enabled, this is to make sure that the keys are used only once. Bytes to bool, app keys used deprecated. That's clever. It's very clever.
So throw away your key when you're done.
Yeah, it's a one use only permission. Note, whenever modifying the storage layout here, it is important to update the valid storage layout function in its respective mock contract to ensure that it doesn't break anything or lead to unexpected behaviors of the layout when upgrading. Cool, yeah, so that's what we were talking about earlier. That's normal. Constructor takes the bool non-upgradable and app whitelisting enabled. So I would say false and true, generally.
Yes.
And then we set those two immutables. And once that's set until we maybe do the, if this is true, then we can upgrade.
Yes.
Cool. These are just the proxy things. So obviously you need your initialize function, iSuperFluid governance gov, external initializer.
That's for the upgradable.
Yes, yeah. And then gov equals gov. Then it has the UUID, which just returns the bytes 32, which is the ketchak of this SuperFluid implementation string. Update code, address, new address, external override, only governance, very important. And this is something I'm noticing in a lot of DeFi protocols, and I just want to make a little note of to the viewers. Some people, obviously, like most people would use only owner here. Why they are using only governance is it's the same as only owner, but there's no renounce ownership function, which is quite good because you don't want to be the owner and then accidentally renounce your ownership and then no one can update the code, no one can do any of the only owner functions. So a lot of people are switching to using only governance instead of only owner.
And I suppose that allows a bit more freedom, a bit more space to...
Yeah, you just know you're not
going
to accidentally delete your permission, basically, renounce your permissions, yeah. So if non-upgradable, revert non-upgradable. If the new address is a non-upgradable deployment, revert host can not downgrade to non-upgradable. So you can't go back to the old one if it wasn't
upgradable.
Non-upgradable. So the new address has to be an upgradable address as well. And then you update code address, new address, that internal function, which we would inherit from your UPS proxyable. I bet you someone who was watching that, who uses Slack, just checked to see if there was any Slack message with those mouse. Cool, get now, it returns block.timestamp. Makes sense.
Oh.
Governance, get gov. Replace governments. Governments equals new governments.
Cool. That's my power coming back.
Oh, nice. Yeah, we have something called load shedding in South Africa where we both are based. So our power goes out for like 6 hours of the day in like three 2-hour splits. And I can hear all of Myles' devices coming back to life. So you're on a hotspot?
No, my UPS was...
Oh, cool. Yo, my UPS blew the other day, and then I got some batteries and tried to fix it, and then
dude,
I think I broke the batteries last night. Anyway.
I don't know what I would do without it.
Yeah. Cool. This is for agreement whitelisting. Register agreement class. Cool. So this is great because they might bring out new agreements. Like a friend was telling me that they might bring out a a mixture between the two. I'm not sure what it's going to be called yet, but it's one-to-many, but it's a stream.
Oh, cool.
Very cool. So they'll probably call register agreement class when they bring that. So it takes an iSuper agreement class logic, external only governance override. Byte32 agreement type. Okay, so it gets the agreement type, which is a function in agreement, iSuper agreement. If it's not equal to 0, revert host agreement already registered. So this will probably be a 0 or 1 thing, where 0 is false and 1 is true.
Yes.
And then if the length is greater than 256, max 256 agreements, then you initialize an instance of that agreement class, or you just, define it. Then if not upgradable, if it is an upgradable deployment, initialize the proxy first. So then you go new UUPS proxy equals proxy, proxy.initialize proxy address agreement class logic. Cool. So now you're taking this agreement class address. You take the agreement class logic, which is an instance of iSuper agreement. You get its address, and then you initialize the proxy on that. Agreement class iSuper agreement address proxy. So now that proxy has become a valid agreement class iSuper agreement. That's what we created here, 9156. And then else agreement class equals iSuper agreement address agreement class logic, which is what we pass in.
Yeah. So it's either makes it upgradable, or else it's just normal non-upgradable contract.
Yeah, absolutely. And then it just sets that the agreement class. And if it is upgradable, it sets the proxy to the initialized proxy. So it's yeah.
Yeah.
Cool. Agreement classes dot push agreement class. So remember, we probably they're checking the size here. So it's probably an array of agreement classes that is 256
bytes.
Elements long.
Yeah.
And then sets the indices to the new length. So it takes the new length and puts this agreement type in the mapping. That value is the indices.
The indices. It's just the last
mapping
in the array.
And then it emits agreement class registered, agreement type, and the address. That's nice. Cool. Then you can update. Only governance. If non-upgradable deployment reverts non-upgradable, and then you get the agreement type, IDX, agreement type. So you get the indices. Well, so from the indices mapping, you get the index of the agreement type you're looking for. If it's 0, it's not registered. Cool. Then you do the update code proxyable function call, basically. So they probably call this in their, did they call this in their, yeah, but they called the internal function. Cool. So now we know what that does. Function is agreement type listed, and it returns a bool.
And it needs to be not 0. Okay.
Is agreement class listed, same thing. And it just also checks that the agreement class's index -1 is equal to agreement class. Was this an in? No, sorry. So yeah, obviously it should be the same agreement class proxy address. That makes sense. Cool, get agreement classes. Sorry, get agreement class, you put in the agreement type, and then it should return an iSuper agreement instance. So obviously it can't be 0, but then if it is, you just return you take the index as -1, and then that'll be from the mapping, and then it returns your class. Cool, that's just querying the mapping. Map agreement classes. Ooh, interesting. Has a uint256i and n. Creates memory output using the counted size. So agreement classes equals new agreement. That's cool. So it's of size length.
That's cool.
Makes sense. Add n to the output. So n equals 0. For I equals 0, I less than agreement classes dot length plus I. remember, not I++, I++ I says 2 opcode calls. If bitmap, where is bitmap defined?
I think it's the bitmap library.
Oh, yes, of course. And then you shift 1 to the right of I, so it's 0 now, but that goes, obviously, it increments, is greater than 0, then agreement classes of n++, n plus 1 is equal to agreement classes I. Okay, cool. So you just fill it in.
Wow.
And then they resize memory arrays, which is cool. mstore agreement classes, comma n.
That's an interesting way to use assembly and bit shifting.
It really is. They really do some interesting bit shifting in assembly stuff. Then function add to agreement classes bitmap. You take the bitmap that you put in as a 256 and agreement type, returns the new bitmap. Cool, yeah. This is just bit shifting. So it checks that it's registered, and then it returns either bitmap or one shifted to the right by the index -1. We haven't seen much casting, even though they use safecast, which they'll probably get to. I mean, how big is this contract? Okay, we're like nearly halfway. Remove from agreement classes bitmap. Cool. That returns the and. I'm trying to go a bit faster so that we get to finish this. So the next episode is its own module where we look at how to build a super app using an example. Get super app token factory just returns the token factory. Get the logic. So you first assert. It's not address 0. Obviously, we want to do that, and then we want to, if it's not upgradable, return the address of the super token factory. Otherwise, return the get code addresses of the super
proxy.
Yeah, because now that we've upgraded. Update super token factory only governance, not address 0. If it's upgradable, then you make a new proxy and you initialize that proxy, and then you put the address. Now the super token factory points to the new proxy address. Cool. That's similar to what we saw above, where they were updating the agreement class. So this is actually the same thing as updating the agreement class. And updating the logic, it's the same. It'll call update code, which is just you can look at UPS proxyable in OpenZeppelin. That's where they got this from. Then they app registry, so register app. Put in the config word, external override, and if whitelisting is enabled. Oh, I see. So you can't just do this if you're not whitelisted. Yeah. And then you call register app, which is an internal function you'll see later. Then register app with key takes in a string call data registration key. Get app registration config key, transaction.origin, and registration key, which is what we pass in. And then
that's basically your one-time PIN.
Yes, absolutely. That's what that is. And you get that key. That key only works when whitelisting is enabled.
Yes.
And then you check that the key is valid and not expired using get config as UN256. This, I think, is the address. ICP token address 0, config key, and then if this is less than block.timestamp, revert post invalid or expired super app registration key, and then if not, you register the app with true.
Interesting that they check it against the timestamp.
I was about to say, because they have a function for that.
Yeah.
Yeah, either don't have the function for it or just use the function. Register app by factory takes in an app and a config word. Message changer must be a contract, so they'll check that. They do it. Wow, they do it in
in assembly.
In assembly, but basically they check that the contract size is not 0, that it has code. So UN256 CS, and then CX equals exit code external code size, I think, caller. So that makes sense.
Yes.
And you set that, and if it's 0, then it must be contract, because now it's got 0, it's got no code.
Because a EOA or that wouldn't have code. That would be it would have code size of 0.
Yeah, I want to, sorry, everyone. I just want to remember that you can just do it in assembly like that. Because I often check that code size isn't 0, but this is obviously more efficient. So excuse the screenshot. If whitelisting is enabled, then the config key, you get the config key, then you get the configs. And if it's not an authorized factory, then you revert, otherwise register app. Okay, we're finally at register app. We've called it like 4 times. Let's see what it does. It's an enter. It's private. Takes in a config word, SuperApp. Oh, so this is, oh no, never mind. It takes in a config word, an app, and a bool check if in-app constructor. So that'll be true or false. And then you first check if message sender is transaction origin, revert app rule, superstitions, no rule, app rule, no registration for externally owned account.
Yeah, so it's got to be a contract. It's got to be a host that registers the app.
Cool. Then if you did flag this as true, they do the same thing, and they say if it's not equal to 0, then app rule registration only in constructor. See, so then they're passing in app, whereas over here they were passing in the caller, which is a function call. Kind of gets like the message.sender. Where were we? Here. Otherwise, if so if the word isn't clean or the callback app level is 0, or if its jail bit is not equal to 0, so obviously 1 flagging that it is jailed, then revert invalid config word. And then if you get the config word not equal to 0, it's already registered. And then you add this to the app you add it to app manifests mapping, and then you admit app registered event app. I haven't seen the events. They aren't in the interface, which makes sense, and they aren't in maybe at the bottom.
They're probably at the bottom, yeah.
Function is app just returns this must be a bool. Yeah, it's bool. Checks that the config word is greater than 0. Cool. If it's not, then it's not a registered app.
Yes.
Get app back. This just is a getter. Get app manifest. Cool. Is app jailed? It just gets the
It's good to know.
Allow composite app. So it probably first checks. I'm surprised they don't call is composite allowed in allow composite. Oh, okay. Maybe this means you set it to true.
Yes.
For the target app, you add a composite app. But obviously this will, for now, this is not something that I think is functional yet. Well, like not enabled. Is composite app allowed? Ooh.
So that's probably false right now.
Yeah, it's false for all apps. Agreement framework. Okay, so call app before call back. Takes in app, call data, is terminated in context. Only agreement. We haven't seen this modifier. So events and modifiers must be at the bottom or inherited, probably inherited. And but yeah, that makes sense. It's only so it'll check that mapping to see the valid agreements. Assert valid context. Returns bytes, memory, CB data. So gets callback, passing an app true is terminated call data and context. Returns bool success and bytes memory return data. If success, then you check that it is valid ABI encoded bytes with the return data, and then you ABI to decode this return data. And that's the bytes CB data that you return. Else, if no success, then if is not termination, reverts app rule malformated, else jail app. Okay, so if you make a malformated call app before callback, your app can get jailed.
So I'm guessing malformated app is when you have conflicting when you change the order of the variables in the upgradable.
That might be it, but I think actually that just has to do with the upgrading.
Okay.
The upgrade, having data collisions and not being a successful upgrade, like the proxy won't work. I think this is more it's to do with the context.
Oh, okay.
So if obviously first assert it's a valid context, but if it's not successful when you call the call app, and if it's not meant to be a termination call, then you jailed the app. Something went wrong in the logic.
Okay.
Call app after callback, it's all the same modifiers and stuff. It's the same thing.
It's exactly the same thing.
It just gets a new context from the context, and it says its calls is context valid, which we'll probably see below. If it's not a terminate, yeah, this is the same thing. App callback push. So first we see that the app credit granted is different. That's a new thing the parameter we haven't seen. uint256, app credit used, int256, so it can probably be negative. Context memory, context, decode context, context. Note, we use 1 as a magic number here as we want to do this check once where we are in a callback. We use 1 instead of max app callback level because 1 captures what we are trying to enforce.
Okay.
I really enjoy comments like this note. Cool, so you first check that it is a super app, is an app that's registered. We saw that function earlier, and context or callback level is greater than or equal to 1. Then if it's not a composite app, revert that the composite if the composite app is not whitelisted, okay, because this returns a bool. I thought it returned a 1 or a 0. Then it's not whitelisted, and then you revert. Otherwise, increment the app callback level in the context. Set the call info, call type, app callback context definitions to the call type of the context. Then you make the context equal the uint256 that you put in for app credit granted, and the app credit used, you put that into the context. Then you set the address of the app to the app address of the context. Remember, we saw that earlier. That's how you get that's how they check if it's a valid app in the super app base. App credit token, and set that, and then app context, update context with the new context. Cool. That's really quite elegant.
It's beautiful.
So you push that to the stack. Now there's a pop. Bytes call data context, int app credit used delta, context decode context, and then you plus equal app credits used delta to the context app credit used. So you put in the change, and then you update the context. Context use credit, only agreement assert valid context, returns memory new context, and it just app credit use more, so it's just
increases the credit used.
That's used, yes. Cool, and then jail app, only agreements, assert valid context, and you just call the internal jail app. Contextless call proxies, call agreement. Cool. Takes in the message sender address. Interesting that they don't just derive that. iSuper agreement class, call data and user data, internal, clean context. I'm not too sure. We must find these modifiers that they inherited. Is agreement, did you pass in the agreement class? Cool. Okay, so there's a byte for one, and they're saying beware of big Indian. Agreement, selector, call utils, pass selector, call data. Then they build the context data. Cool, so they're just initializing everything. Here's where let's go timestamp.get now. Well, timestamp equals get now, not
block that timestamp.
Wonder why. set everything to 0. Then there's bool success, and then they call external with replace context. And if this, and then they'll return success. If it's not a success, you revert from return data, else you clear the stamp, context stamp 0. Call agreement just calls the internal. Call application, this is the internal now. Call app action, sorry. Takes in a message sender, app and call data. Is app active? App is valid, app action, cool, and clean context. Those are the modifiers. It builds the context data. Cool, we've seen that. And then success. If success, context ABI.decode the return data in bytes. If it's not a context, the valid context, revert with the app rule that context is read only. Else revert from return data, revert from return data with the return data passed. Remember that's a bytes. And then clear the stamp. Then there's call app action, the external, and that just calls the internal. And the note, the modifiers are called in the internal. So this has no modifiers. I would almost swap that, or put, because if you don't, because what I think they're wasting a tiny bit of gas here, maybe, because you're calling something that, no, I guess not, because it doesn't pass if you fail here.
Yes.
Contextual call proxies. Cool. Call agreement with context. That'll just, call the agreement. It checks that it's the right address, sets the old sender, then context.message sender equals message.sender. Then it updates the context, which we have seen before. Bool success is call external with replace context. We saw that earlier. And then if success, decode the return data to make the new context, assert that it's valid. And then context equals decode context, new context. And then you set the message sender to the old sender. That's cool. And then you update the context. Else call utils.revert from return data, passing the return data bytes. And then call application with context. Cool. So you can call an agreement with a context or an application. And I think this is more or less the same. Just it's calling
the agreement.
Yeah, instead of decode context. Okay, cool. That just calls internal. Is context valid? Cool. Calls internal. Batch call. So it takes in an array of operations. It's internal. And then it iterates through the operations, and it's if it equals approve, ERC20 approve, then you do that. Else, if it's transfer from, then you do a transfer from.
Oh, that's very cool.
Otherwise, if it's ERC777 send, then you do an operation send. That's cool.
That's very
and then it can be a super token upgrade or a super token downgrade or a SuperFluid call agreement or a SuperFluid call app action. And then you get the actions and probably, you call app action, which is an internal. Otherwise, revert unknown operation type. Batch call calls internal, batch call that we just looked at. Forward batch call, same thing, but with get transaction signer as passed into the as the message sender.
Yes.
Is trusted forwarder will return a bool. Cool. Version recipient return v1. Jail app. Cool. This is the internal one. The external just called this, and it just checks that it if the jail bit is 0, probably set it to 1. Yeah. Update context. Cool. This probably just over here sets ABI encode, ABI encode all of these. And then context stamp equals the catch-check of the whole context. Decode context, that's the opposite. Cool, then is context valid? It just checks the length and the catch-check of context is equal to that context stamp. Then there's an internal call external with replace context that got called a lot. So assert that the target, which is an address you pass in, is not address 0, so you can't target yourself. Call data, replace placeholder context, cool. Then you call external with replaced context. And then if it succeeds, you Only if the return data length is 0, then you revert app rule, it's malformated. This is called callback. Is static call is terminated. Call gas left before is a gas left function, and then is static call first does a static call, and then where the gas is passed in is equal to the callback gas limits, and then the call data is also passed in, and then it returns success and return data. Else, don't do a static call. If failure, 63 is a magic word to avoid.
Okay.
Yeah, and then yeah, it just checks that there's enough gas. Else reverts SuperFluid need more gas, and then replace holder context. I just want to see how much is left. Okay, cool. Maybe we can get through it in like a minute. Is what we have left. Cool. This is just we saw this. They just replaced the holder context, so it's like a swap of the two contexts.
It's
and
like
they do that through two M stores in assembly. Yeah. Sorry, what were you going to say?
So it's like when they initialize it, they initialize the context to a blank context, and then when you add the app, then it writes the context.
And then these are just the modifiers, which we've seen, and we know what they will do. Like they're all self-explanatory. Is app action? Yeah, they just check that. Awesome, cool, great work. Next week we'll look at how to actually make a super app, some examples in their repo that they supplied. And yeah, I hope everyone has a good Friday. Thank you for watching another episode of Solidity Fridays, brought to you by Linum Labs.
I really enjoyed hosting with you, Tam. And I'll see you guys next week.